Hello, I'm Erik Scheurer from the University of Stuttgart, and I will present our paper Detection Defenses, and I will present our paper Detection Defenses, an Empty Promise Against Adversarial Patch Attacks on Optical Flow. Adversarial patch attacks are useful for evaluating the robustness of neural networks and highly safety critical, as they can be printed out and change the behavior of neural networks in real-world scenarios. A small part of the input is optimized to maximally disturb the output of the evaluated method. Detection defenses then aim to detect the modified pixels in the input and reduce the impact of those pixels by removing them from the scene. However, because the detection mechanism does not always find the correct pixels to remove, the defense destroys information in the scene, reducing the method's accuracy. For the prediction of 2D motion from an image sequence, also called optical flow, the proposed defenses partially succeed in defending against patches. Yet they have not been tested with state-of-the-art methods or with defense-aware patch attacks. In our paper, we train adversarial patches that are able to avoid detection of the defense and evaluate them on a range of different networks. We see that the loss of accuracy using the detection defenses actually hurts the method's robustness. So far, 2 detect and remove defenses have been proposed for optical flow: local gradient smoothing and inpainting with Laplacian prior. Both methods detect adversarial patches due to the higher gradient magnitude observed in those patches. The areas with high gradient magnitudes are then replaced by the defense to reduce the impact of those patches. LGS applies gradient smoothing, while LP inpaints with Thaler's algorithm. The patches in the bottom images are correctly detected and mostly erased from the image. However, when evaluating the method's robustness, the full prediction pipeline should be taken into account. So far, the defenses have only been tested with patches trained on the neural network itself, but adding a defense creates a new method that consists of the concatenation of defense with the network. This new method has to be tested with patches that are trained with neural network and defense in mind, not just the optical flow method. We contribute an optimization scheme that is able to bypass the shadowed gradients of the defense using the known backward pass differential approximation, and avoid detection by adding a loss term penalizing high gradient magnitudes of the patch. The new defense-aware patches are noticeably smoother than the unmodified variants, as can be seen on the right. The defense-aware patches are successfully able to avoid detection and render the output flow unusable for the downstream tasks in the bottom 2 flows. We measure vulnerability of the network with the pipeline robustness, which we define as the distance of the defended flow to the flow resulting from the images that have been attacked and defended. This plot on the right depicts the robustness in relation to the accuracy of the method. The optimal method would be in the origin of the plot, with a low prediction error and a low distance between attack and no attack. Different defenses are depicted with different symbols, and colors are optical flow methods. The red data points show state-of-the-art methods, namely RAF, GMA, and Flowformer. These lose in accuracy as well as in robustness when defending. This reveals an interesting realization about the effect of detect and remove defenses. When removing the patch from the image, the defense removes information from the scene. In cases where a defended method receives unmodified input, the output will be of lower quality than the undefended method as seen in the top 2 flows in the red box. For this reason, if a noisy patch pulls all defense effects onto itself, the rest of the image will be mostly unaffected, and the output is closer to the original. The optimal parameters for optimization for accurate methods produce an almost arbitrary noise pattern to exploit exactly this weakness. For illustration, the middle patch on the left is the LGS-aware patch for Flowformer. A manual patch consisting of the checkerboard pattern behaves in the exact same way as shown in the last row of the flows. Based on our findings, we create guidelines for publication of new defenses to extend the best practices in classification to pixel-wise tasks. First, you should always report quality changes together with the robustness of your method. Second, this robustness should not be the robustness with regards to existing attacks, but the method that you propose should be able to withstand attacks that are tailored to the new defense. Lastly, if the method that is improved is part of a larger pipeline, such as optical flow being part of action recognition pipelines, then the subtasks should be evaluated separately, in our case optical flow. We hope that you check out our GitHub repository, where we publish our full source code in addition to more evaluated patches. Thank you for watching, and check out our paper for an in-depth analysis and more visualizations.